Now this is a lesson on the introduction to inverse functions. Examples. Consider the function y equals e to the x minus 3. In part A we're going to determine the equation of the inverse function, stating its domain and range, and in part B we're going to do some curve sketching. Solution. Let's write down the original function firstly, y equals e to the x minus 3. Now the inverse function. Okay, the notation for that is f to the minus 1 outside of x, okay, the inverse function. And basically all we do there, the y and the x, we basically swap around, simple as that. So to do that we eventually get that x equals e to the y minus 3. And then from here what we're going to try to do is try to make y the subject. So let's take that minus 3 over to the other side, becomes plus 3. So we'll have x plus 3 equals e to the y. Now, as I said before, we're trying to get y by itself, need to get rid of that e. So to do that, we're going to take the logs of both sides. So on the left side, we'll get the log of x plus 3, and e to the y, take the log of that, simply we're left with y. So that's we've got the inverse function there. Inverse function is y equals log of x plus 3. So we've done the equation there. Now we've got to work with domain and range. Well, the domain and the range, I'm going to write that down, but we will come back to it. It's much easier to find domain and range after we've drawn a sketch. So we need to draw the sketch in part B. Let's move to that. So the sketch, y equals e to the x minus 3 firstly. We draw our x and y axes, and e to the x minus 3 is effectively our normal y equals e to the x, but instead of cutting through at 1, we drop it down 3. So hence it's cutting down at minus 2, and the asymptote will be through at minus 3. Okay, so the line y equals minus 3 is the asymptote there. Now our inverse function, it's a log graph. Okay, so it's going to look like that. It's cutting through at minus 2, and it has a vertical asymptote at x equals minus 3. Now a couple of features of the graph. Our original function had as an asymptote y equals minus 3. The inverse, if we swap it around, the asymptote is x equals minus 3. Our original function had as a y-intercept of minus 2. Our inverse function has an x-intercept at minus 2. So basically you can see the x's and y's are swapping around. Now the other thing it asks us to do is show the line y equals x. Well, it's a special sort of line y equals x. In the case of inverse functions, you'll notice that the original function and the inverse meet, okay, they intersect along the line y equals x, okay, so that's an important concept to understand. Now we're jumping back to part A, we need to find the domain and range, okay, so we look at it, the domain firstly, it starts from minus 3, doesn't quite touch minus 3 does it, so it's got to be greater than minus 3, so there we have it, x is greater than minus 3. The range though, well, if we look at our y values, the graph is going to keep on going down, and in terms of it's still going up, okay, and even though it seems to flatten down a bit, it will still keep going up. So the range is all real y. Terrific. So that's our graph there, our original function and the inverse. Moving on to part 2 now, consider the function f of x equals x squared minus 2x. Part A, we need to sketch y equals f of x, showing the x and y intercepts and the coordinates of any stationary points. Part B and C, some more work to do. But let's start, okay, we are writing down the function. So part A. Now even though it says f of x equals x squared minus 2x, for the purposes of graphing certainly, we'll say y equals x squared minus 2x. And we can factorize that. And in factored form we can realize it's going to be a parabola, and the intercepts are at x equals 0 and x equals 2. So let's draw that firstly. Okay, there are intercepts there at 0 and at 2. So we draw the parabola through those points. Now the coordinates of any stationary points. Well, certainly we don't really need to do any calculus here because it's a parabola, straightforward. We can realize that it's going to occur between 0 and 2. So the vertex or stationary point occurs when x equals 1. So let's substitute x equals 1 into the equation there. We get that y equals minus 1. So x equals 1, y equals minus 1. Let's mark that in on the diagram. 1 minus 1. Now part B, we need to find the largest domain containing the origin for which f of x has an inverse function. Alright, let's just move some things around a bit so we've got a bit more room. Now if I draw a horizontal line as such, you can see that it is cutting the parabola in two spots. Now for the function to have an inverse function, it can only have a horizontal line cutting it in one spot only. So we draw another line there, again, cuts it twice, so no good. Keep on moving down, you can see it's going to cut it twice all the time. So we'll need to restrict the domain. Okay, all of those horizontal lines cutting it twice. So we need to restrict the domain in such a way that it contains the origin. So we're going to choose the domain such that it includes x equals 0 and any horizontal cuts the curve at most once. So that area I've highlighted there, that would satisfy that criteria. It includes the origin, and if we were to construct horizontal lines through that, it would only hit that part of the curve once. So we're going to restrict the domain then to be x is less than or equal to 1. Now we need to state the domain of the inverse function. So we consider firstly the range of the original function. Now if we look at it, we can see that it's starting at -1, that's the lowest point, and then it keeps on going up. So the range of the original function is y is greater than or equal to -1. Then the domain of the inverse function is x is greater than or equal to -1. So you can see there, simply swapping the x and y's for the domain and ranges. Part D, find the coordinates of any points of intersection of the two curves y equals f of x and y equals the inverse function of x. Part E, Part F to follow. Now let's concentrate on Part D firstly. Now y equals x squared minus 2x, our original function. Now we can say that y equals f of x and y equals the inverse function of x intersect along the line y equals x. So hence we can find the point of intersection by finding where y equals f of x, okay, the original function, meets y equals x. So that's our original function. We're trying to see where it meets y equals x. So i.e. we're going to solve x squared minus 2x equals x. So solving that quadratic, let's take the x over, subtract it. X squared minus 3x equals 0. We need to factorize that. Then solving that, we get that x equals 0 and x equals 3. Now of those two answers though, if you recall our restriction on the domain, the restriction was that x was less than or equal to 1. So as a result, let's get rid of x equals 3, so therefore x equals 0. And when x equals 0, substitute back into the original, we get that y equals 0 as well. So we have an origin there, x is 0, y equals 0, therefore we can say that the function and its inverse intersect at the origin. Part E. On the same diagram, sketch y equals the inverse function. So let's bring our diagram back, our original diagram. Now recall that we restricted the domain to be x is less than or equal to 1. So as a result, I'm going to get rid of the rest of the graph. Now if we consider the point 1 minus 1, that's part of the original function. Now if we were to reverse that and get the point minus 1, 1, okay, so we just basically swapped x and y coordinates there, that will be part of the curve of the inverse function. Now if we draw the line there, y equals x, it's important to understand it basically is a mirror image on either side. The function and its inverse is a mirror about the line y equals x. And to illustrate that, let's just move this down a little bit, and we're going to spin around the page. So we've got that mirror line right down the middle, okay? So you can see it's a vertical line. It's much easier for you to understand what we're trying to do here. Now the graph then would look like that. The inverse function, if you have a look at it, you can see that the line y equals x is the axis of symmetry between the two curves. Okay, back to its normal orientation. So let's label that y equals the inverse function of x. Our final part, we need to find the equation of the inverse function. So let's write down our original. Now our inverse function, we simply swap the x with the y, so we'll end up getting that x equals y squared minus 2y. Now we need to eventually make y the subject, but we'll have a perfect square involved here. So let's write down this, y squared minus 2y equals x. So all I've done is just sort of rewritten the order there. Now we're going to try to complete the square. So in brackets there, we'd certainly have y squared will give us that y squared, and then we'll have minus 1. Now if you have minus 1 squared, we've effectively added 1, so we must also add 1 to the other side as well. So on that right side we have x plus 1. Now if that's what the square is, let's take the square root. Therefore getting y minus 1 equals the positive and negative square root of x plus 1. And last step there, take the minus 1 over, becomes positive 1. Therefore y equals 1 plus or minus the square root of x plus 1. Now at the moment we've got two equations there. Okay, the plus and the minus will give us the 2. So the inverse function is one of, it's either going to be y equals 1 plus the square root of x plus 1, or it's going to be y equals 1 minus the square root of x plus 1. So let's call these equations 1 and equations 2. Now let's go back to our graph there that we've drawn a moment ago. Now we can see from the graph that a point like minus 2, 8 is on the original function. Alright, so we can say that minus 2, 8 satisfies the original function y equals f of x. Now as a result, this point here is 8 minus 2. In other words, we've just swapped the x and y. So we can therefore say that 8 minus 2 must satisfy the inverse function. Alright, now armed with that knowledge, 8 minus 2, if we substitute that into equation 1, you will find that no, it doesn't work, it's not valid. If we substitute 8 minus 2 into equation 2, then it does work. So we can say that 8 minus 2 satisfies equation 2 only, so therefore the inverse function is y equals 1 minus the square root of x plus 1. Excellent. Well, a fairly lengthy lesson there, but you may need to look over it again. Okay, some pretty interesting concepts there. But in any case, that's the end. Good luck with your questions.